Hello and welcome everyone to the Topological Complexity Seminar, which is part of the Applied Algebraic Topology Research Network. And today I am pleased to introduce our speaker, Petar Pavešić, who's coming from the University of Ljubljana to tell us about the covering type of spaces. Take it away, Petar.
Okay, thanks a lot, Jesus. I'm really glad for this opportunity to talk to the topological complexity community. Even if I'm cheating a little bit today, I'm not going to talk about topological complexity, but about some other topic which is a bit similar but still different. So you can take this as a kind of advertising propaganda if you want. And I mean, let's see if you have some ideas that might help us with study of this topic. So let me share the screen. Okay, and close this. So hopefully you can all see the my screen. So this is everything handwriting. I hope it's readable, but anyways, I'm going to explain most of the things. Okay, so let me start with the basic definitions. A covering type. This is a relatively new invariant, new concept. Even if you want the ingredients were here, like for the last 68 years, it could be easily defined much earlier, but it wasn't. So the definition is the following. So if you have any space, you know that an open cover is said to be good if all elements and also all finite intersections of the covering are contractible subspaces. And the typical examples that we normally think of are like geodesic balls in a Riemannian manifold, or open stars of vertices in spaces which can be, I mean, with the triangulations. That's two typical examples of good covers. And here we will always assume that we have some good cover. So we are going to avoid things like a Hawaiian earring and so on. So we assume that we have a finite good cover for all spaces. And so I'm not going to make exceptions that something is infinite or something. And I mean, most of the time. Okay, so the first thing that we can easily observe is that the minimal cardinality of a good cover of a given space is not something that is homotopy invariant. In fact, you can represent like a wedge of three circles in this way as a one skeleton of a tetrahedron. And clearly, if you cover it by stars of vertices, you have four elements in a good cover. But you can represent it also in this way, and then it requires some checking. But the minimal good cover, it turns out that has 5 elements, and this is an example of a way that you can split it. Think of it as a bit extended, so you have an open cover. Okay, so a few years ago, now it's almost 10 years ago, Max Karoubi and Jacques Weibel defined a covering type of a space as a minimum of a cardinality of a good cover I mean, among all spaces which are homotopy equivalent to X. And so this is a standard way how you take a quantity and make it a homotopy invariant. So this is clearly a homotopy invariant of a space X. I mean, if you have spaces which are homotopy equivalent, they get the same minimum, of course. Okay. Now the first immediate thing that you get from this, you know that if you have an open cover, a good open cover with some partition of unity, assume that you have some, then there is always an Alexandron map from X to the nerve of this thing, and it can be written explicitly. And the nerve theorem says that if the cover is good, then the this map is a homotopy equivalence. Okay, so that's a standard theorem. And we will all usually think of this as saying that the nerve of a cover is just a form of a homotopy triangulation of X. So, I mean, you have a triangulated space which is homotopy equivalent to X, right? So this in particular means that if you have a paracompact space, so you have subordinated partitions to your nice covers, then this covering type of X can be interpreted by as a minimum number of vertices in a homotopy triangulation of X. Now that's a minimum up to homotopy, and then clearly, again, immediately, if your space is actually triangulable, so you have some triangulation, then the covering type of X is a lower bound for what I denote as delta of X, and is defined as just the minimum number of vertices in a triangulation of X. And in a sense, this simple observation was kind of a motivation for most of this like beginning early work on covering type, because we realized that the covering type is a kind of a homotopy invariant measure of a size of a triangulation of some geometric space. So some starting computations were done by already this initial paper by Karoubi and Weibel. So they computed precisely the covering type for graphs, and you get something like this. So the covering type of graph is this expression, so 3 plus square root of 9 minus 8 times the Euler characteristic of the graph halves, and then you round this to the next to the first integer that is bigger than that. That's just by direct construction and some estimates of the Betti numbers. This is one result, and then they also estimated the covering type for surfaces or closed surfaces, and simply just saying that that's smaller than the minimal triangulations, and it is known since I think 60s and 70s. There are results saying what is the minimal number of triangles of vertices that you need to triangulate a surface, a closed surface. I mean, separate for orientable ones and non-orientable, but you get some number like this, and this number can be decreased by 1 for some exceptions. So this is not the precise value. Okay. And they also had some lower bound, which was about the half of this number, and they didn't say anything about what is the precise value. But just a few years later, Borghini and Minian proved that most of the time this value is precise. So most of the time, for most surfaces, the covering type of a surface is equal to this number. Then there are 3 exceptions for which it is smaller by one. This is the double torus, the Klein bottle, and the non-orientable surface of genus or hemigenus 2. When it is smaller by 1, the number of vertices in a triangulation. And Borghini and Minian showed that for surfaces, the covering type of a surface equals the minimal number of vertices in a triangulation for all cases except for one, which is remarkable. So for the double torus, I mean torus, the genus 2 torus, a genus 2 orientable surface, I should say, the covering type is 9, while the minimal number of vertices in a triangulation of this genus 2 surface, orientable surface, is actually 10. So why is this remarkable? This simply means that, I mean, normally you think that if you have a closed manifold, then a triangulation of a closed manifold, a minimal triangulation, should be something very efficient. It is hard to think of something which is homotopy equivalent to this with a smaller number of vertices, smaller number of simplices. But it turns out that in this specific case, there is a smaller model. So there is a two-dimensional simplicial complex homotopy equivalent to the genus 2 orientable surface, which has one vertex less. And that's essentially the only example that we have. And mainly because it is hard to compute both of those numbers. So there are very few spaces for which, I mean, there are few infinite families, but then just some exceptional spaces for which we know exactly this minimal triangulation, and also a small number of spaces for which we know that what is precisely their covering type. But still, this is like my first open question. You will see, I mean, questions and problems will be in green. So my first question is, can actually this be arbitrarily large for closed manifolds? So, I mean, if you have a manifold, can the minimal triangulation be as far as you want from the minimal homotopy triangulation? We have no idea. Essentially, almost the only example is this one. Okay, so this is the first. Then there was a collaboration with Dejan Goetz, Václav Marcantovic, and me, and we published several papers in the last 5 years, obtaining different lower bounds for covering type, some based on Lustenich-Schnirelmann category, some based on cohomology products and weighted cohomology products. Results related to fundamental groups, to group actions. So different things that gave us various results about estimates of covering type, lower estimates about the covering type. And maybe just to give you some flavor how it works, I will give you the simplest one. So the estimate of the covering type based on Lustenich-Schnirelmann category. And the argument is as follows. Oh, one thing, since I'm doing this full screen, I don't see if anyone raises hands or something. So please stop me if you want to ask questions, and you are welcome to ask questions whenever you want. But I need to...
Yes.
I profit, Petar.
Yes.
It's Massimo Ferri.
Oh, hi, Massimo. Yeah.
Can you go a bit above, because there is a striking similarity between the inequality that you have for the CT of surfaces with the one for a chromatic number of a surface.
That's exactly that one. I mean, there are guys. So Ringel and Jungermann proved that those the chromatic number is okay. It is exactly, or by just the chromatic number is this +1, right? Or no? It really
it looks exactly like that. I remember the 7 and the 49, and is there a reason for that? I mean,
they essentially these are dual problems. So asking what is the minimal graph that you can, a full graph that you can embed I mean, the minimal genus of a surface in which you can embed certain graph is just the dual question of what is the minimal triangulation of that surface. So that's absolutely not a coincidence. This is exactly the same number with, as I said, with 3 exceptions, 1 orientable and 2 non-orientables that you can find in those papers. So yes, for small triangulations, there are some exceptions. If you have enough room, then it is exactly the chromatic number.
Thanks a lot.
Yeah. Okay. And thanks for the question. That was yeah. Okay, so let me show how we can use Lussner-Schneemann category to estimate covering type. So assume that you have some categorical cover of a space, right? With n sets. So my Lussner-Schneemann category here is non-normalized because it's more convenient because it's just counting, right? So from this, you know that since the category is n, you know that the homotopy dimension of the space is at least n minus 1. And thus you have certainly n elements in this cover which intersect. But since this is a good cover, right, then you know that by Nair theorem, their union is homotopy equivalent to a simplex, so it is contractible, so it is a categorical subset. So if you remove those, right, then you get a smaller, I mean, some smaller set of open, I mean, some smaller family of open sets, and its category decreases at most by 1, by usual argument. So then its category is at least n minus 1. So you can find n minus 1 sets with non-empty intersection, and then you repeat the argument. So their intersection is non-empty. Their union must be contractible. It is categorical. You remove them and continue this thing. And eventually you get this sum, which gives you this estimate that the covering type of X is at least this quadratic expression in the category of the space. So it seems that we have some result that the covering type increases at least as a category, Lussner-Schneemann category of the space. But don't expect too much from this because, you know, whenever you have some fixed number, not 1, because then everything is contractible, so at least 2, then for fixed n, you have only finitely many spaces whose covering type is up to n, because these are just like subcomplexes of an n minus 1 dimensional simplex. But of course, you have infinitely many spaces which have a category smaller than n, right? So this means that if you look at covering types of all spaces with category up to some n, this is some unbounded set. I mean, you have arbitrarily big numbers there. So it can happen that you have a smaller category but bigger covering type, in spite of the fact that covering type increases at least quadratic. So, and a specific example, if you take a sphere, its category is always 2. You take the projective plane, its category is 3. But if you compare the covering type of RP2 is the minimal triangulation of RP2, which is with 6 vertices, the known one. And here, the covering type of a sphere is at least dimension plus 2, so it is bigger for all n's which are bigger than 5. So essentially, you have infinitely many spaces whose covering type is bigger than this fixed one, in spite of the fact that the category is smaller, right? But I mean, nothing contradicts this quadratic increase, just that you have many more. You have some kind of a finer, in some sense, a finer invariant. Okay. So by slightly adapting the previous argument on category, we get also some cohomology estimate, a similar one. So if you have a non-zero product, then it turns out that the category of X is at least this sum. So dimension of one element and then twice the dimension of the second one, and so on, plus n plus 1. Clearly, it's convenient to order them by increasing order. I mean, by increasing dimensions. it is almost the same result if you take, if all elements here are of dimension 1, but it gets much better if those elements are of higher dimension. So maybe the most convincing application that we had is to estimate the number of vertices in the triangulations of Grassmannians, because you know that you have generators of different dimensions. So it turns out that the minimal number of vertices and also minimal number of all simplices increases really fast, which actually explains why there are only very few known explicit triangulations of Grassmannians, which is kind of a problem when you compute characteristic classes and things like that. So that's, I mean, and the increase is really incredibly fast in the sense that for relatively small dimensional Grassmannians, you can get millions, hundreds of millions, or even 10 to 20 or 30 power number of simplices, which is just amazing. That the minimal number of simplices in any triangulation of a Grassmannian space. Okay, so this is essentially the list of the results that were obtained, say, up to this year. So before continuing, I mean, I'm going to talk about more recent developments later, but let me talk a bit about what are the main open problems, and maybe you will have some ideas how to work on that. So the first problem is, you know, we have a feeling that this is like Lucenich-Schneemann category theory before 50s or before 1950s, 1960s, where the Gania and Whitehead descriptions were done. So in terms of sections or extensions or homotopy extensions. So maybe the first problem would be to find some nice description of the covering type in terms of sections of some vibration, or maybe several successive vibrations, because I think that, I mean, after thinking a while about that, I think that maybe we need more, I mean, more than one vibration to express this. This would be really very nice. That this would probably open many possibilities for computation or estimates for the covering type of X. And then the second is maybe a smaller, more defensive problem. As you've seen, we have relatively good lower bounds for the covering type of X. But at the moment, we don't have any good upper bound for covering type of X. So if you have a general space without any nice description, we don't have anything general to say about the covering type of X. It is a bit different if you have some information about how the space is constructed. And again, so let me just list a couple of examples. So for example, if you suspend the space, then its covering type increases at most by 1. If you attach a cone by an n-sheeted covering map, like when you make cyclic groups, Moore spaces and things, then the covering type of the cone is at most the n type, so the number of sheets times the covering type plus 1. And it's relatively easy to guess how to prove those. Also, those are kind of obvious. The covering type of X cross Y is at most the covering type of X times covering type of Y. But this is really a very bad upper bound. Or the covering type of a wedge is the covering type of the sum of covering types, but maybe you can save some vertices, so you can decrease it by some small number. But you know, this is really almost all that we know. And if you think, I mean, maybe return it here, you know that there are very, very simple, I mean, Riemannians have a nice and relatively small CW decompositions and enormous triangulations, which essentially means that most of the problem is not in the number of cells, but how complicated are the attaching maps. So this difference essentially kind of measures the complication of, I mean, the difference between attaching map being a continuous map or being a simplicial map. And we don't have a good measure for this. So, I mean, this should be somehow included in the picture. But there are also other problems.
Petar, can I ask you a question?
Sure, please.
Precisely there, where you saying that, however, the covering type for a Cartesian product, a Laganea,
and no, that it's not the sum; it's a product.
It's
right?
a product. It's just on the two lines above. Is is the product. Okay.
Yeah. That's but yes, I mean this is just a number of. If you think of a triangulation, if you make a triangulation of a product, I mean, you get the product number of vertices, right?
Right.
That's, I mean, the simple-minded one.
So do you have an idea if you can replace a plus or to get something similar to a Ganea conjecture?
Almost certainly we cannot obtain plus because it increases quadratically. So plus is certainly not a good operation, because then I mean, try to plug in the quadratic increase, and I mean, it would be linear on one side and the quadratic on the other side. No way. If you compare category and the covering type.
Right.
It won't work.
All right. And then you say that it is pretty much not a good estimate. Can you be
it can be very
specific
bad
about what
estimate.
you meant?
Yeah. I mean, yes. So the problem is that category, in a sense, is a good estimate when you have small triangulations. I mean, category squared. But then when you have like big triangulations or big Betti numbers with the same category, that gets so essentially. There are estimates using Betti numbers, which are not very good for small triangulations, but asymptotically get better than those by which are using like cohomology products. So it's like it goes in two directions. One of them goes vertically through category and the cup length, and it also goes horizontally if you have like a bigger genus or big Betti numbers. So there is an interplay with in the study of polyhedra and convex spaces and triangulation, there are things like lower bound theorem and generalized lower bound theorem, which take into account Betti numbers. So you have a combination of two kinds of formulas. But I mean, the main problem with the lower bound theorems, that's probably the deepest part of the theory, and it's really a classical topic, is that they have good estimates for higher dimensional simplices, but there are none about the number of vertices. So these results about the relation with the category is, I think, I mean, the only general result that gives something there as an input. So it's interesting that you have an old classical, well-developed theory which was related and then improved using this new concept of covering type. But so I mean, are there other questions or? Yeah. So let me continue. So there are also other phenomena that happen here, and maybe it is this question. So if you think of a covering type of X cross Y or X wedge Y, and yes, we have some relatively weak upper bounds, but one would expect at least these lower bounds, like the category of X and category of Y, or perhaps even the sum, or here, category of X and category of Y. So, I mean, if you make products, sorry, not category, covering type. So the covering type should increase. And also if you wedge things, the covering type should increase. But I mean, and the reasoning behind that is we are normally used that if some space, say X, homotopy dominates some other space, then something that is a homotopy invariant of, I mean, some homotopy invariant quantity of X should be in some sense bigger than the same quantity of Y. This is kind of feeling that if X homotopy dominates Y, we feel that X is some sense bigger than Y. But this is not entirely true. So let me give you two examples. First, okay, you maybe know that there exist spaces, complexes, such that X is not homotopy equivalent to a finite CW complex. But when you multiply it by a circle, it becomes homotopy equivalent to a finite CW complex. And this is related to the Wall's finiteness obstruction. And there are explicit examples. So obstruction is an element in the K group of the group ring and things like that. I mean, I have here some details, but maybe we should, we should rather go to other things. So this just means that you have a space whose covering type is infinite, but when you multiply it with a circle, it becomes finite. So it drops dramatically. Okay, you can ask whether something like this can happen for finite complexes. I didn't try with products, but here is an example for wedges. Now, this one is a bit more involved. So we can consider this is some basic family of group presentations. This is taken for a paper by Danuta Kovačić, I mean, some 10 years ago. So you put all those relations, and for different I, you get different presentations. It turns out that they are all the presentations of the threefold knot group, but the corresponding to each presentation, you have an associated two-dimensional complex. So those are complexes which have this as a fundamental group, but they all have different second homotopy groups. So they are not homotopy equivalent. But when you wedge them with 8 spheres, then all of them become homotopy equivalent. So that's some classification theorem by J.C. Whitehead from the 60s, I think. Now, this is very interesting. Of course, now what happens, you have this infinite family of spaces. You add one sphere and the second sphere, and some of them become homotopy equivalent after a while, but all of them become homotopy equivalent when you add 8 or more spheres. So this implies, I mean, this just means that you have an infinite family of spaces such that when you add one, so you just take the penultimate one before it stabilizes, right? So you have an infinite family of spaces which are non-homotopy equivalent among them, but when you add one sphere, they become homotopy equivalent to some fixed two complex Y. Okay, now, but these two complexes have some covering type. And if you have sufficiently many those YJs, eventually their covering type will become bigger. So you see that you have a space such that the covering, so the covering type of you have infinitely many two-dimensional complexes, such that the covering type of the complex is strictly bigger than the covering type of the complex with one two-dimensional sphere wedge. Okay, so now this is very strange, right? As you see, both examples, both families of examples that I gave you are just heavily related to some complicated phenomena related to the fundamental group. And I tried, but I was not able to find any example which is simply connected. So here's my next problem. Is it true for products, for wedges, or maybe even more generally, that if X homotopy dominates Y, then the CT of X is bigger or equal than CT of Y if all spaces involved are simply connected? So does this really relate to the fundamental groups, or there is something more complicated behind it? So this is my second question. Okay. And now I have, what's that, about 10 minutes to for the last part, some recent developments, which are very much in the spirit of studying the related. So you have some homotopy invariant, and then you make it an invariant of a group. So this year there appeared the paper, I think that the preprint was from the last year, maybe 22, by Babenko and Mula. So they defined the KW, the Karoubi-Weibel invariant of a group G. Well, I mean, you can think of two ways to approach this. You can say, okay, there is some invariant of G is just CT of its respective Eilenberg-MacLane space. And this kind of limits the scope, because then it must be a finite, usually you expect that it is a finite complex or something like that. This one is much wider, so you can take the Karoubi-Weibel invariant of G as a minimum of the covering type of a complex K, which has this K as it has G as a fundamental group. And it's kind of obvious that you can always assume that K is a two complex, otherwise you just take a two skeleton. So the minimum is achieved on two complexes. And also, so you can check or ask whether this Karoubi-Weibel invariant of G is just the covering type of a corresponding Eilenberg-MacLane space. And Łukasz Michalak proved that for surface groups. I must mention that, so this is actually kind of mentioned or stated in the Babenko-Mula paper, but without proof. And I think that they didn't realize that there is something non-trivial to prove that. So the proof here is non-trivial. You need to prove that given a surface group, there is not a better model than the triangulation of the surface. There is not a better two-dimensional complex which gives that fundamental group. And in view of the Whitehead's theory that I mentioned before, this is absolutely not obvious. But anyway, the question is then when it is true that the Karoubi-Weibel invariant of G is the same as the covering type of the corresponding Eilenberg-MacLane space, assuming that it is a finite CW complex. So we know that is not true in general for some asymptotic reasons. So I mean, we can estimate the increase of both of those, and we know that probably from dimension 4 or maybe dimension 5, for dimension 4 up, you get different values. But for small cases, you get all examples that we can think about are they are equal. And so this seems to be a reasonable question. Okay. Now they computed a lot of estimates for different groups, usually groups which have some explicit constructions. So for Artin groups, for Coxeter groups, and this includes like free abelian groups and some cyclic groups and so on. But still, nothing precise. The only exact values that we know for the moment are free groups and surface groups, and nothing else. Everything else is just estimate. Okay. So, and mostly estimates are kind of asymptotical. Even I think that we can improve some of those. No? On the other hand, Goetz and Marsantovic and Michalak and myself, we are going from the other side. We are trying to classify groups which have a small Karoubi-Weibull invariant, this KWG. And this is always, whenever I mention this, is up to a free factor, because you can always add some edges and increase the free factor. So technically, we are talking about groups of Kurosh rank, Kurosh free rank 0, right? So far we were able to completely classify all groups that have. Okay, here is this is wrong. This is okay. Sorry. Here it is Karoubi-Weibull. Of G up to 8. And the list is the following. So it is a cyclic group with 2, 3, and 4 elements. Then a free abelian group of rank 2. Then the semi-direct product, which is just the fundamental group of the Klein bottle, and the trefoil notable. So these are all groups that can appear on essentially on 8 vertices. And then we try to do this for 9 vertices, and the problem explodes. We are using quite powerful computers, and so far it is a work in progress. We managed to find the following groups. So cyclic groups. So these are new with respect to those of CT8. So we get cyclic groups of order 5 to 9. Then the free products of Z2 and Z2, this is the dyadic group. Then Z2 and Z3, this is the projective special linear group over this. Then Z times Z2, Z times Z3. Then dyadic group on 6 elements, the Bounce-like solitaire group 2, 2, 1. And then the fundamental group of the following 4 surfaces. So the genus 2 orientable and genus, hemigenus 3, 4, and 5 non-orientable groups. And part of a motivation for us was to find among those the following group. So the binary icosahedral group, we didn't. The program is not concluded, so it is possible that the covering type of the Karoubi-Weibull of the binary icosahedral is 9, but we kind of believe that it must be 10. And this is related to an open question by Björner and Frank Lutz about the minimal triangulation of the Poincare sphere. They conjecture that it is 15. So far, it is known that it's bigger than 12. Now we know that it is at least 13 by this result, and this result probably, I mean, it will imply that it is at least 14, so the gap is much smaller now. Okay, so this is what happened, I think, during this year, at least the things that are published on arXiv or unpublished our results. So this is my last question, and I think it is also the right moment to stop and say thank you for to the audience.
Well, thank you very much. I invite everyone to unmute yourself and show our appreciation for the speaker.
Thank you.
Great, thank you very much. So, are there any questions for the speaker?
I have a question. Thank you very much, Petar. That was really interesting. Maybe it follows from what you said, but is there an inequality for covering spaces?
Yes, it is. And of course, if you have a finite, that one is obvious, n times the covering type, because of course, every triangulation, I mean, it's an upper bound. Of course, I don't know if it is, I mean, it is at most n times the covering type of the base. But it can be much smaller. We don't know.
But you have examples where the covering type of the cover is greater than the covering.
No, I mean, just think of you just take the double cover of a sphere to the projective space. Now, Sn, so the n-dimensional sphere has covering type n+2, right? Projective space, it is an open question, but it is about 2 to the n. So it was a long-standing conjecture that it is at least 2 to the n, the number of vertices. But quite recently, I think Adiprasito, Karasev, and I think Avakumov produced something which is slightly under exponential, so it's slightly less than exponential, but still huge. Still about, I mean, you can think about 2 to the n. So you have 2 to the n, but then a double cover which has n+2 covering type. So everything unwraps, and
I think what I was getting at is, do you have an inequality like you have for LS category, where the covering type of the upstairs is less than or equal to the covering type of the downstairs always?
You mean for the category? Isn't the case that the category of covering space is the same as the category of the base?
Oh, it can go down, like for spheres and projective spaces.
Yeah, you're right. Yeah, that's.
But for TC, we know that it can go up.
Yeah, sure.
So I was wondering if there was a general fact for covering type.
So I mean, I'm almost sure that it can go up, and as you see, certainly it can go down. There is okay, I don't have an example on the top of my head, but oh yes, I have, because if you take say genus 2 surface, then its covering will be a higher genus surface, so it will increase. We have precise numbers.
Yeah. Okay, thanks. Yeah.
Yep. Other.
Well, I have a question. Here in your very last slide, you were using CT, but I think you wanted to use the Karoubi
Yeah. I mean, all of them are Karoubi wireless, of course.
So I was wondering, in any of these cases that you have a very much idea of, well, a description of what is happening for the Karoubi Weibull invariant, what is the situation for the CT?
I mean, okay, what is CT? CT is not defined for the group. We have kind of two possibilities. Either you say invariant of the group is the minimal 2 complex, all right, or the CT of the
Space.
Of the Eilenberg-MacLane space. But it really doesn't make sense, because, for example, if you take a cyclic group, it's an infinite complex. It is, of course, possible that it's an infinite complex with a finite number of vertices, but the covering type will be infinite. I mean, I don't. Okay, it's conceivable that it is finite, but I just think that it's not a good definition. I think that definition that Babenko and Mula give is the right one. I mean, is in the spirit of this invariant.
Yeah.
But maybe I should comment something. You certainly feel that this covering type is a bit like strange, like the geometric category, right? The minimal number of contractible spaces that you need to cover a space, right? But you know, the geometric category is strange in a okay, it's not homotop invariant, so it can be arbitrarily bigger than the category of the space. But when you like minimize over all spaces with the same homotopy type, it becomes just the strong category, which is then at most by one bigger than the category of the space. It is equal to the cone length, so it becomes tame, right? So what is strange here is that this thing has some irregular behavior even when you stabilize. Of course, you can take what is the minimal number of I mean minimal size of a covering of a good cover for a fixed space. This is something that Karoubi and Weibel in their first paper called strict covering type. And this one is even more complicated, even more irregular. So it's, I mean, it's not a homotop invariant. But here you take a homotop invariant and it's still strange. I mean, how it is possible that you have some good cover and then you add a sphere, a two-dimensional sphere, and it becomes smaller. And I mean, the difference can be arbitrarily big. What's going on here? That's a strange guy. But it seems finer than the category, right? Because there are many more values that you can achieve.
That's weird.
Yeah. I mean, I think that, as I said, this gives just the if the things develop somehow, we are in this initial part of history. We need some homotop invariant, some sections, some extensions way to describe this concept to proceed, right?
I never thought well
That's
of the
almost like
number 8, and now I think it's a smart number.
Is there any relationship to the idea of ball category for manifolds, where you cover by sets that are homeomorphic or diffeomorphic, I don't know, to balls in Euclidean space? I mean, it won't necessarily be a good cover, I guess, right? Because you would need some sort of convexity to get the intersections to be contractible, or maybe not.
Okay.
No, I think so.
So I may say it also in a different way. You know, when you take a space X and then and you take some categorical cover, its nerve is a simplex, is contractible.
Right.
Right. So that's I mean the most. I mean this is the initial stage of approximation of a space, right? A good cover is in on the opposite side. I mean it gives you the exact homotopy type. So there seems to be some, I mean, successive approximations that are behind it. That's why I said there might be some sequence of fibrations whose section kind of approximate the covering type. But I mean, I'm just simply not smart enough to find it. That's
could you start asking for covers where any pair of the intersection of any pair is contractible, or any set's contractible and any pair, you know, and then build up.
That would be something. So we kind of tried it. You know, there are special or variants of the nerve theorem which say, okay, if you have that all intersections are, say, up to k connected, then the Alexandrov map is up to, I don't remember, k or k minus 1. equivalence and things like that. Yes, so that's especially Dan Gold's work on that in his PhD. So essentially, if you think the picture when you see when you see if what kind of cover you take is just this Meyer-Vietoris spectral sequence, right? The page of the Meyer-Vietoris spectral sequence tells you at least up to I mean homologically, right? Tells you how many your intersections are like homologically trivial, or I mean then intersection of pairs, of triples, and so on. You can kind of proceed with them. So yes, but again, I mean, I was thinking about it. I didn't find anything useful, but it doesn't mean that there is nothing. Just